The second diamond anniversary lecture. So for some of you, actually, some people were asking, what does diamond mean? Well, those who are not married that long, of course, did not know what it means. So it stands for the 60th anniversary, and so CSL is 60 years old, 60 years young. We say it's 60 years young because looking forward to the future, there is definitely more than, not many of us will see that, but there's more than 60 years in the future of CSL and maybe multiples of that. And so this is, we thought that the 60th we should have some special celebration and a year-long one. And in the spring semester, we decided to invite 3 distinguished speakers to kick off the 60th anniversary celebration event. And then in the fall, in October, we'll have a sort of a summit or a culmination of those events, a one-day event, a symposium. And so you'll hear more about that later in the coming weeks or months. So this lecture is the second in the series. We had one exactly 2 weeks ago. And there will be a third one in about 5 weeks from now, all on Mondays at 4 o'clock. And I'm very pleased to introduce Professor Miroslav Krstić from the University of San Diego, University of California, San Diego. And he has been there for quite a number of years. And he is a very prolific author. He has 8 books by my last count, unless he has written one last night. And he has worked in many areas or topics in control systems, the network control, and partial differential equations, delay systems, and so on. And today's talk is going to sort of bring together a number of these topics into a very sort of an appealing framework, which will be on network control systems, nonlinear systems, and with delay playing an important role. So let me give you a little bit of background on Miroslav's honors and recognitions that he has received. His current position is a named professorship. It's an ALSPA professor in UCSD, and he's the founding director of the Cymer Center for Control Systems and Dynamics at the University of California. He graduated from, again, University of California, but in Santa Barbara, and spent a couple of years at Maryland, and then UCSD lured him away from there, and then he has been there for since the mid-90s. And he received most of the awards that NSF bestows on young faculty, that the FICAS as well as the Career Award. He also received the ONR Young Investigator Award. And from the Control System Society, he received the Axel D. Best Paper Award, and from the American Automatic Control Council, he received the Sharp Paper Prize. And at UCSD, he is the very first recipient of the research award that the engineering college there started, and which is a major accomplishment. He's a fellow of IEEE and IFAC, and he has been, and is still, senior editors in the IEEE Transactions on Automatic Control, as well as he's an editor in Automatica, and I interact with him quite frequently in that capacity. So today's, I don't see the title here, but it is the state-dependent delays and nonlinear control over networks. Miroslav.
Thank you very much.
Thank you very much for the kind introduction, Tamer. And I want to say that this is probably the highest professional compliment that I've received so far, having the privilege to give this Diamond Anniversary lecture. So thank you again for this opportunity. Let me address one question that several people have asked me. Was I a student at Illinois for a little bit of time before Professor Peter Kokorovich went to Santa Barbara? The answer is, unfortunately, I did not have that opportunity. I contacted Peter just as he was on his way to Santa Barbara, and he said, well, do you want to come to Santa Barbara? Because at Illinois, you'd have to choose another advisor. And so I never was a student at Illinois, but I do consider myself a member of, I wish to consider myself a member of the Illinois family. So this should be departmental, or rather laboratory-wide talk that would be of interest to the general audience. Unfortunately, what I do is fairly technical, so I've chosen to speak on something that would be at least intriguing to most people, if not of interest professionally to everybody. So my topic of research over the last few years has been control of nonlinear systems with delays. And networks is one of the contexts in which such problems arise. But I have to be honest that the emphasis here is on nonlinear systems with delays, especially with delays on the input. Now, the topic of this talk is state-dependent delays. And this goes back to me reading an article a few years ago in which what I consider a particularly sick intellectual problem was posed of controlling a system that has a delay that is not only time varying, but the delay in this state equation depends on the value of the state itself. So not only is the problem infinite dimensional, but the state space, which is infinite dimensional, is so volatile that you really hardly know what the state space is. And I thought that maybe one day I'd like to look at this problem, but there are so many other things I need to do first, namely develop some delay results for nonlinear systems, for time varying delays, and so on. And I finally got to getting over this hurdle of state-dependent delays a few months ago, just as Tamer contacted me, and I chose that this is a topic that I think would stimulate the high-level audience, such as at Illinois. Now, what are physical motivations? For example, in the context of control of systems over networks, you can imagine that a particular efficient scheme for transmitting data would be one where if the state is smaller, you let that particular control loop wait longer and have a longer delay than the loops that involve states that are larger and where the need for control is more urgent. So this would lead to state-dependent delays. My talk will be almost all on continuous time systems, so it is not directly applicable to such networks with asynchrony and with time-varying delays, but that connection can be made. Another example that is physical, before I actually show you some examples where it's also physical, but this one everybody can relate to, is the example of driving an automobile. So for example, if as a driver you're faced with a significant disturbance that you need to correct, particularly large disturbances will affect your reaction time. The reaction time, your reflexes are pretty constant until the situation that you're in starts getting dramatic, and then you start getting kind of paralyzed. And that is a state-dependent delay in that context. Now, a list of engineering applications of delay systems, which is an obligatory part of any such talk, is this particular list that goes into process control, combustion engines, machining, rolling mills, which is an example that Peter Kokorovich contributed to this list, telesurgery, and control over networks that I mentioned. My talk will be focused on nonlinear systems with input delays. You can have state delays as well, but the most difficult problem is the one where you have to overcome a delay in the actuator, or where a delay on the sensed variable interferes, which is a similar problem. So I will focus primarily on input delays. Now, to get to tools for controlling nonlinear systems with long, time-varying, and state-dependent delays, I have to go one step at a time. So I will introduce the ideas that get us to nonlinear control systems with state-dependent delays, basically by going through a progression that I went through over the last few years, namely starting with LTI systems with constant but long, arbitrarily long delays, then extending that to LTI systems with time-varying delays, then going to the nonlinear case with constant delays, and finally wrapping it up with state-dependent delays. The last item will be about 40 to 50% of my talk. So let me start with LTI systems. Many of you probably know about predictor feedback, but I will remind you and introduce it for others. It's a very neat and elegant tool which needs to be, if you haven't seen it, then you need to see it in the proper way as what it is. So consider this system, x dot equal to ax plus bu with a delay on the input. And the idea is that this delay may be very large and the plant may be unstable. How do you compensate that? Well, starting with the basic assumptions that the pair AB is controllable or at least stabilizable, and that a nominal controller for the AB part, a nominal stabilizing controller is known, then the predictor feedback law is given by this formula. There are three things to be said about this predictor feedback law. First, the bracketed term is actually x at time t plus d. This is truly a predictor. This almost may look as a non-causal controller, but it is not, because it is given as a feedback controller. It is given, this prediction is given using the current measured state as an initial condition, and using the history of the control over the past d time units that has been committed already to the plant as the input. So this is truly a feedback controller. This is not any kind of an open loop or non-causal controller. Finally, it is important to observe that this is an infinite dimensional controller, because in addition to this state feedback x, you have the integral of the control history, which makes this controller an infinite dimensional controller for the plant that itself happens to be infinite dimensional. If you want some intuition, well, you can look at, for example, the red term. If the plant is unstable, this controller is not going to be just kx, which is not a controller that is aggressive enough for an unstable system. But in the presence of delay, the matrix exponential will increase the gain, and you will get, after the control kicks in, to stabilize that system. Now, where does this idea come from? So there's a history of new, really significant contributions happening in this area every about 10 years. First, Otto Smith introduced the Smith predictor in 1958-59, but this tool is not applicable to unstable systems. It works for systems that are already asymptotically stable and where you just need to compensate a long delay. Then 10 years later, a result that I don't know, probably almost nobody knows about except for David Main himself, who brought it to my attention. He developed this predictor result 10 years before the people who are credited with it. However, he published it in this electronics letters journal. It was a 2-page note, and it even tackles the output feedback case using an observer-based predictor design. Anyway, nobody really knows about that. This result is generally credited to Manitius and Olbrot in their transactions paper of 1978, and this approach is referred to as finite spectrum assignment. Why finite spectrum assignment? Because you completely eliminate the effect of the delay after d time units. which means that the spectrum of the system consists of the poles of the ODE that you've placed at arbitrary locations, plus the poles of a transport equation of a pure delay, which is fed with a zero. And those poles are poles at negative infinity. So that's why it's called a finite spectrum assignment. Anyway, for us, I will refer to it as predictor feedback. Now, these two results that I mentioned proposed a controller, and they stated what the eigenvalues of the system are, namely just a finite spectrum in the left half plane. But they did not pursue any construction of a stability proof in a Lyapunov setting. Now, why is that important? It is important because you cannot study stability, and especially you cannot study robustness without having some kind of a Lyapunov function, without having a characterization of stability in the time domain rather than in the frequency domain. So for such a study, you need a Lyapunov functional. Turns out it's kind of tricky to find the Lyapunov functional. What you need is a suitable transformation of the infinite dimensional part of the system that allows that study. So this is a transformation of the actuator state, which you see here with a variable, with a time-like variable theta varying from t minus d to the current time t. This is an infinite dimensional transformation that happens to mimic in the continuum setting the so-called backstepping approach, which most people have heard about and which was introduced by Peter Kokorovich and some of his students almost 20 years ago. This transformation allows the construction of a Lyapunov functional. The Lyapunov functional after that complicated transformation is a simple one. It is just an L2 norm suitably scaled by this time like variable of the new actuator variable W plus the Lyapunov function for the ODE part of the system. I will use enhanced versions of this basic idea throughout my talk. Now, what are the benefits of having a Lyapunov function? I mentioned robustness, but robustness with respect to what? Robustness with respect to just about anything you can think of. External disturbances, parametric uncertainties in A and B, and so on and so forth. But the most critical one, the trickiest one, is robustness with respect to the delay itself. This kind of a result, the opinion on whether something like that holds for the predictor feedback was split about 50-50 in the community. It was just not provable, nor was even an intuition available that would be solid enough. Anyway, with a Lyapunov function like that, such robustness can be proved. In fact, these are two robustness results. It's a completely different situation. If the actual system has more delay than you believe, versus less delay that you believe, because in one of these two cases, your controller is introducing an extra bit of infinite dimensionality by feeding too long of a history of the input into the closed loop system. Anyway, such result can be established, and the stability holds in the sense of this L2 norm on the state of the closed loop system. A result really requires two proofs, one for positive delta D, the other one for negative. Or it can be boiled down to a single proof, but in the sense of an H1 norm, namely a norm that in addition to the L2 of U contains also L2 of U dot. Anyway, let me now move on to time-varying delays. This is an interesting topic. The basic idea for dealing with systems with time-varying delays was introduced in a paper by Zvi Artstein in 1982, which immediately went into considering LTV systems with TV delays. And it's a mathematically logical thing to do. If the delay is time varying, let A and B also be time varying. The only problem is that in that fully general case, you cannot get any explicit results. 10 years later, a researcher in Finland came up with an explicit result for LTI plants with time-varying delays. It was just a control that was worked out without any stability analysis, nor even a feasibility analysis of the controller, by which I mean, are the gains of the resulting controller bounded or do they go unbounded under some conditions? Let me show you what the controller is. So suppose you have a time-varying input delay. And think of this function phi of t as a delayed time function. It is the current time minus the delay time d of t. It is important that I introduce this notation for phi of t as a single variable. And the reason for that is that the controller needs an inverse function of that function phi of t. So the controller is given here. And the controller depends both on the delayed function, on the delay time phi, and on the inverse of that delay time phi. This phi inverse function is like a prediction time. The time at which your control that you commit now to the plant will actually kick in, will hit the plant. Phi inverse minus t is the prediction horizon of that controller. Anyway, I will get to that. You see here, this is simply the variation of constants formula, again applied to the initial state x of t, which is measured now, and evaluated over a horizon phi inverse minus t. So let me, this diagram shows what these times are. If the dotted line, that is the time variable, t. The solid line phi is the delay time, t minus d of t. And this phi inverse is the inverse function, and you see what it might look like in a case where the delay time has this undulating periodic pattern. Here's an example. The simplest one I can think of, a scalar but unstable system with a time delay that has that sinusoidal pattern. In the response of the state, you don't see any effect of that time, because before the control kicks in, the system runs in open loop. After the control kicks in, the delay is completely neutralized. But in the input, you see how that delay is being, the time-varying delay is being compensated. You see this undulating pattern in the input. This is just an illustrating example. What can one prove? One can prove exponential stability in the sense of this L2 norm. So the state consists of a Euclidean norm of the OD plus an L2 norm of the actuator memory over the time interval equal to the delay. The initial condition is the same norm, but at time t equal to 0. There may be a large overshoot g, which depends actually on the shape of the function d. The lowercase g, the exponential decay rate, is independent of the delay because the delay is actually compensated, so it has no effect on the delay rate. Now, what are the conditions of a result like this? This is important to see because this whole, all the constraints that arise in the time-varying case will also come up in the state-dependent case. There are 4 conditions on the delay, and these are the least restrictive conditions that, as you can get in the setting where you have a time-varying delay. First of all, the delay needs to be non-negative, which means causality. That's an obvious condition. Second, the delay needs to be uniformly bounded, and that simply physically means that all inputs eventually reach the plant. The fourth condition is that d prime, the delay rate, is bounded from below, which means that the delay cannot just instantaneously disappear. It can disappear only gradually. The key condition, though, the most important of these 4, is that the delay rate is bounded by 1. Why 1? Well, physically, that happens to have the meaning that the input signal never gets reversed. That you always keep, the plant always keeps experiencing newer and newer inputs sent to the plant rather than going back to the older one. The Achilles heel of this whole idea of time-varying delays is the following. that the inverse function, phi inverse, this function phi inverse, which is the inverse of the delay time, happens to be a future value of the function phi. In other words, you need to know the delay a certain length of time in advance in order to be able to invert this function and know the prediction horizon. So that's a problem. And I thought that there was an insurmountable obstacle for state-dependent delays, because I thought there's no way you could know such a time for a system that is running in real time, and the state depends on the input, which is yet to be computed, and so on and so forth. Now, let me forget the time-varying delays for a moment and step back to constant delays, but now introduce nonlinear systems. This will be very, very brief, but one big conceptual step comes up. So let me consider systems of the form x dot equal to f of xu. I don't know why this dot.
It's there.
Huh? It is there. You can see it.
Just
Okay.
small, but we can see it.
That's in Acrobat Reader, but in the preview it shows up nicely. Anyway, so x dot equal to f of xu. Completely general nonlinear systems with two reasonable assumptions. Suppose that for the nominal case without the delay, a stabilizing controller is known. Maybe a locally asymptotically or globally asymptotically stabilizing controller. In general, I will assume globally. And for getting a global result, I also need to assume that the open loop system is forward complete. In other words, it doesn't have a finite escape time. It may be nonlinear, the state may be getting large, but it will not explode before the control gets to kick in. This is a natural assumption. If your system may have a finite escape time and the control is delayed, it's a hopeless scenario. That's all natural, but here's the tricky part. What is the controller? The controller, the first line of the controller looks extremely simple. It's just a nominal controller, but using the predictor state. This is what this P is. P is replacing the current state X. And how is this predictor state calculated? It is calculated from this integral equation, which is just a replica of the ODE using the state X as an initial condition. Now here, this looks trivial, but actually what's hiding here is different than what it seems. This is not to be viewed as some sort of a filter, as a dynamic component to this feedback law that you calculate. This P is simply a transformation of the current state X. This is not dynamic feedback. It's a purely static feedback where you should think that at each time t, you recompute this variable p using the history of the committed input u and the currently measured state. The question is how to compute this, and when is it possibly explicitly computable. In general, it is not explicitly computable, but we can prove everything that we need to prove, namely global stabilization under these assumptions for a system in this form. Now, what is really conceptually the form of this predictor feedback? I will try to make this clear for a particular class of systems where an explicit form for the predictor can be given. This is the class of the so-called strict feed-forward systems. It's a narrower class than strict feedback systems. There aren't too many of those, but they're interesting systems because they're not feedback linearizable, and yet they can be globally stabilized. Anyway, consider this example. This is an example in which x3 can be analytically obtained from u because you just need to integrate. x2 can be analytically obtained from x3, which you just found, and u, which you have. And x1, likewise, can be analytically obtained from the previous two. And here's what you get. I'm showing this only to appreciate the structure of this predictor, not the details. So the predictor is simply an algebraic formula involving the measured states state variables x1, x2, and x3, as well as the integral Volterra type operators, some linear ones and some nonlinear ones, quadratic ones, of the control history over the past d units of time. So this is truly a full state static feedback, where you have to think of u as a state of the system. This is the actuator state. It's not it's not to be thought of as memory, as a part of a dynamic compensator. So that's typically conceptually what you deal with when you're dealing with nonlinear predictor feedback problems. Now let me switch gears for the moment significantly. Let me go to not this discrete time, but to sample data problems to illustrate how this predictor feedback can be applied to a relatively real-looking system. So consider the model of a non-holonomic unicycle, a mobile robot controlled over a network. I will show you two things in this example. First, how the predictor can be computed explicitly, and second, how this predictor-based feedback can be implemented using a sample data controller. Actually, there's a third thing also. In addition to the input delay and sampling, I will also introduce sensing delay. And to make the notation simple, because I have the sampling time, the input delay, and the measurement delay, I will take all three of these quantities to be the same, capital D. This is really not making my problem much easier except notationally. So I have these three quantities to deal with. So here's the controller that we have designed. You cannot quite take an off-the-shelf controller that people have designed for the stabilization of the unicycle in continuous time. You have to develop a specific sample data controller, and then for a controller like that, you have to compensate the input delay and the measurement delay. So here's how you do that. Use sample data feedback with a sample and hold implementation of the control inputs V and omega. So V is the forward speed, omega is the angular velocity of the vehicle. You use this standard transformation, which is used for converting the unicycle into Brockett's non-holonomic integrator, and then you use this predictor formula. This predictor formula employs the measured state of the system, which is delayed by D, as well as the history of the input over the past two sampling periods, because you have to compensate both the input delay and the measurement delay. Now, what I have not shown you yet is what the feedback law is, what these nonlinear functions K1 and K2 are. They were specifically developed for this particular result. This is a new sample data stabilizing feedback law, which was developed by my collaborator Iason Karafilis from University of Crete. And this fellow is really the best kept secret in nonlinear control. An extremely talented researcher in nonlinear control and delay systems. So this is a sample data feedback law, which is compensated for which predictor-based compensation is designed to compensate for the input, sensing delay, and the sampling. The result that is provable is that for arbitrarily large delay and arbitrarily large sampling time D, the closed-loop system is globally asymptotically stable at the origin. And in fact, this particular feedback law achieves a deadbeat stabilization. In other words, in 3 plus 2 D intervals, you achieve a zero solution. Okay, let me now get to state-dependent delays. This is the main subject that I want to cover today. So there's a number of delay systems where the delay is state-dependent, including ones that I've mentioned already, as well as milling processes, rolling mills, engine cooling systems, some population dynamics, and so on. This work is done in collaboration with a student of mine, Nicolaos Pekaris Liberis. So let me now go back to the x dot equal to f of xu systems. But now this d is not constant, and it's not explicitly dependent on time using a known delay function, but it depends on the state x. This problem is very tricky even for linear systems. The moment this state-dependent delay shows up, the system becomes nonlinear, irrespective of the ax plus bu structure. What is the challenge? So here's the challenge. This is the key conceptual challenge. The prediction time, the predictor state is the value of the state at the time when the control applied at t reaches the system. But you don't know when this control will reach the system because it depends on the delay time evaluated at that yet to be determined prediction state. It's a chicken and egg problem. It seems impossible to resolve. But it turns out there is a way. By rescaling the time, by figuring out exactly how the time variable is affected, because the time really gets distorted here. The time is no longer just a simple t or phi of t. The time becomes a function of the state. And this can be accounted for. So now the predictor state is found from an integral equation in which the vector field f is divided by this red expression. 1 minus the gradient of the delay function times the vector field itself. You see this this magic 1 appearing in here. The point here is that this gradient times f must not exceed 1. That amounts to the control not starting to run in reverse. It can be shown that this simply is x of t plus the prediction time. So that is the controller. Let me now illustrate how all this works before discussing how this is to be analyzed. Here's a simple scalar system. And I'm introducing a delay that is dependent on the square of the state. This is a very aggressive delay. The larger the state, the more unstable, the larger the state, the more the input gets delayed. It looks like a hopeless problem. And indeed, this system is not globally stabilizing, even though it's linear. I would like to illustrate that negative aspect of the result. The positive aspect of the result are these solid curves. Starting from initial conditions for x up to about 0.43, the control eventually kicks in. You see this kink, and then you have an exponential decay and the delay is perfectly compensated. But if the if the initial condition is larger than 0.43, the control will never kick in. This is the function phi, t minus the delay d of t. You see how it eventually gets reversed, and the control never reaches in, never kicks in, and the state goes to infinity. So this illustrates that's my disclaimer. This is what you cannot ever achieve, but local stabilization you can achieve. Now let me discuss further why this result is not global. If you look at the evolution of the prediction horizon, namely the delay function of the prediction state, it is governed by this OD. And from the possibility of division by 0, if gradient d times f gets too large, you see that the prediction time might go to infinity, which means that at some future time point, the direction of the input signal will get reversed and the input will never kick in. So the conclusion there is that in order to study this system and establish at least local stability, the key condition is a condition the gradient d times f be smaller than 1, or smaller than some conservative bound c, which may be some number between 0 and 1. What is the meaning of this condition? This is a condition on the solutions of the system. What is the meaning of that condition? I call it a feasibility condition of the controller. If this condition is violated, the controller becomes infinite and yet doesn't kick in. That's essentially what it is. It's a feasibility on the controller. So it's a local result. So let me show you what the meaning of this local result is. The plane in this picture is the state space of the system. The state space of the system is infinite dimensional, so it's certainly not R2, but I have no better way to represent it. So the state space is the vector space X plus the function space for the input history U. This is my best attempt to represent the state in the plane. So a local result means that I can determine a ball of initial conditions from which, after a possible excursion outside of that ball, the solution will converge back to the origin. Now, there is this feasibility boundary, which is a set on which the control blows up and goes to infinity. The true initial condition certainly is on the other side of that boundary. And the true region of attraction. The true region of attraction may have a form, for example, like this. On one side, the region of attraction is bounded by some surface, which is kind of hard to imagine in a function space, but it is some open set. And on the other side, it is bounded by the feasibility, by the boundary of the feasibility region. This set FC is a conservative estimate of the feasibility region. The stability result obtained is a local uniform asymptotic stability result in the supremum norm for U. So it's not in L2. It's very hard to get results where the norm of the state is L2, but it can be obtained in the supremum norm. So the meaning of this result is that if the initial condition is in a ball of some radius, and I can control the size of that ball by controlling how conservative I take this C relative to the true boundary of the feasibility region. So if the initial condition is in this ball B0, then a stability estimate in class KL is available. The assumptions, I've already stated them: forward completeness and global uniform asymptotic stability of the nominal system. But it's important to say what the assumption of the function D is. It's a very, very weak assumption. D is simply a non-negative continuously differentiable function of the state. So there's nothing restrictive being imposed on D. Now, how is this result proved? This is very, very interesting and very tricky. This picture actually describes how such results are proved even for ODEs. You would have this kind of a picture even if the state space was R2 or Rn. So to prove this kind of a result, you have to determine a ball within, a ball around the origin that is contained within the region of attraction, and then further restrict the initial conditions based on the Lyapunov function, or functional in this case, for the given system, such that starting from initial conditions in B0, you never exceed B bar, and therefore you never get out of the feasibility region F1. So what I have to do now is do all of this, but in an infinite dimensional setting. The steps are the following. Some of them are really important, and many of the other ones I'm skipping. There is this key transformation, the infinite dimensional backstepping transformation. It's a transformation that shifts the true actuator state into a new transformed actuator state through the predictor state, which is a vector. That's that. And that transformation is the key, because after that transformation, the closed loop system has a very convenient form where it consists of a disturbance that goes away in finite time, perturbing a system that is globally uniformly asymptotically stable. For that system, we can prove asymptotic stability in the standard KL setting. In other words, we can find an upper bounding function that decays in time as time goes to infinity to 0, and is a class K function of the initial condition that overbounds in the same norm, the norm on the state. Now, that's not enough because our actuator state is not W, but it's U. So we need to establish norm equivalence between the norms on the target state, W, and the norm on the original state, U. And that norm equivalence can be established using these class K functions for upper bounding and lower bounding the U state in terms of the W state. Let me skip this. Finally, to complete the proof, I need to show that given the ball B bar, which I construct to be inside the set FC, I can find a ball B naught of initial conditions such that the solutions never exceed B bar and never exceed FC. And this is done by doing estimates on the solutions of the predictor integral equation and so on. So that's the gist of the analysis of this problem. I will move forward now. So I have a few examples that I think will end this on
There's
yes.
I have a question. So, you showed this D prime condition is important.
Yes.
So I was thinking, because you have a particular form of controller, the predictor-based controller,
Yeah.
could you modify that form somehow, or is it intrinsic to any feedback controller? Because you were assuming a particular form of controller, this particular form of controller. Can I?
So yeah, let's say in the linear case. Well, I wouldn't know. I don't know any other way to approach even a linear problem with a state-dependent delay. This is the one I know at this point. So, yeah, I don't know if it could be if this idea of treating the time like that could be applied in the setting of another delay control strategy other than predictor. So I have 3 examples to show you. The first one is maybe the most complicated. I'm going back to the unicycle. So I'm now introducing a state-dependent delay on the unicycle with the goal of stabilizing the unicycle to the origin. And one could imagine that the controller to the unicycle is at the origin, and the delay depends on the distance of the unicycle from the origin to which this controller wants to attract the unicycle. This is really contrived to be non-trivial, and it's not completely without a physical motivation. So the delay grows with the distance from the target position. Now, a different controller is employed here. This is a more conventional controller introduced in 1992 by Jean-Baptiste Pommet. It's a time-varying controller with some sines and cosines. And to compensate the state-dependent delay, this predictor, explicit predictor formula is given here, along with this division by this red term that compensates for the state dependency of the delay. A more interesting thing to look at is the trajectories of the system. On the right are the trajectories of the system in which you have not compensated the delay. What happens is that as the system starts, it diverges along this spiral. It just does not, interestingly, it does not randomly go unstable, but it goes away from the origin in this spiraling. That's how it gets confused in a particularly nice to look at way. Whereas with predictor feedback, you achieve the nominal behavior. The nominal behavior would be to perform this parking maneuver, and I'm sorry that it gets zigzaggy. That's the nature of this problem. If you want to do stabilization, you cannot do exponential stabilization for these classes of systems with smooth feedback. In the uncompensated case, the delay just grows linearly. In the compensated case, as the state goes to 0, the delay itself eventually reaches 0 because it depends on the distance from the desired equilibrium. Second example. I want to say that global stabilization is not always unachievable. There are some conservative situations where global stabilization might very well be achieved. And they do not correspond to making a condition that the delay is uniformly bounded. It's actually the condition that the delay rate is bounded by 1 that needs to be satisfied. And that's a tricky condition because the delay rate depends not only on the state x, but also on the input u, which is inside of f. So it's a really, really unlikely to be randomly satisfied condition. But here's one example that illustrates it. So this is a system which is not linear. It's linear in x, but it's nonlinear in u. And this is a convenient normalization of the right-hand side to make everything work globally. The delay here is a monotonically increasing function. You can almost think of this delay as the Lyapunov function for the system. It's a monotonically increasing function, but it does not grow linearly. It grows kind of slower than linear, logarithmically. This was all constructed so that everything works out globally. The transient is quite illustrative. In open loop, the state grows exponentially. Then the control kicks in. And the nominal system evolves according to this equation, which happens to have a solution that is a backward square root. You see here, it gets steeper and steeper, but when you get near the origin, the linearization takes over and the convergence near the origin is exponential. So this is my last, I believe, last example. So I should say that since the results achieved are local, assuming forward completeness and assuming global stabilization is an overkill. If the result that I guarantee in the end is pretty conservative, then the conditions should be made less conservative. And it turns out, indeed, that's possible. And this is not a linear-like result at all. In this example, I take a system that is not exponentially stabilizable even locally, and that is not globally stabilizable either. So for this result, this solid curve is the trajectory of the system. The dashed curve is the trajectory in the absence of compensation, and the dotted one is the trajectory in the absence of delay completely. So you see here that the control actually kicks in, and then this non-exponential convergence occurs. The region of attraction in the absence of delay for this system is 1 over square root of 2, namely around 0.7. So you see that this initial condition here is actually a very large initial condition. The control kicks in barely when the system escapes the region of attraction. I'm mentioning this because in order to more clearly understand the issue in the general result. So that needs to be accounted for, the fact that control needs to not only kick in eventually, but it needs to kick in while the state is still within the region of attraction of the non-delayed situation. So a local stability result is established, namely, if a region of attraction exists for the nominal case, then predictor feedback will be locally asymptotically stabilizable with some other smaller region of attraction delta, smaller than R. And to prove this, there is this extra challenge that we must estimate the time that the control kicks in, which depends on the open loop solutions. To wrap it all up with a thought on other possible things to do, state-dependent delays on the state rather than on the input are as frequent in applications. In fact, there are really many such situations, and we're working on that. And problems with true asynchrony, with sampling and with perturbations in the sampling schedule for sample and hold implementations of predictor feedbacks are important, and I'm working on that with Jansson Kerfels also. The ultimate robustness, namely achieving input to state stability, a very, very strong form of robustness with respect to delay perturbations, I don't believe is possible. But this is what everybody has, I think, on their mind when they see these results. Can you make this delay not dependent on the state, but a function of time that is uncertain, possibly even stochastic if you can do it? I don't believe that arbitrarily large uncertainties to arbitrarily large delays will be tractable, but disturbances that are delay disturbances that are occasionally quite large, but satisfies some smallness in the mean or some other type of long-term smallness, I believe should be tractable, and I intend to look into that. So with that, I'd like to thank you very much for your attention and wish CSL and all of you a happy 60th anniversary.
Thank you. Before opening the floor to questions, let me mention that there is a reception right after this in 301, the usual place. So we hope to see all of you there. So questions?
You indicated how you go about having space variable delay, but how about the networking aspect actually? So you have state variable delays, but then when you start like putting things together, like in your work, when you connect several PDEs and you have transport, looks like some of these results might play out in that thing, because you kind of didn't really mention the networking angle, and that's supposed to be part of your talk. So could you please maybe link it to your work on transport, on these chains of transport PDEs, where you still need probably time varying. Here you have like varying delays, you know, state variable dependent delays, which is more complicated framework. So that if you can throw in some topology, maybe topology of transport PDEs, or some other more complicated topology where you have graphs, or something like this, so that you, I apologize for pushing you.
Yeah, maybe I've misled.
But you promised to do that, so there.
But putting networks in the title.
Right.
Otherwise, I think I'd have 1/3 of the audience. So I hope I'm forgiven. Forgiven. Let me end that part of the answer. But as far as having cascaded or tree-like graphs of various infinite dimensional dynamics, some of these problems likely would be tractable. Maybe it's more useful if I tell you what I don't know how to do. So for example, I still don't know how to approach nonlinear problems where instead of transport dynamics, namely a delay, I have some other type of infinite dimensional dynamics, perhaps dominated by diffusion and so on. That I really don't know at the moment how to do. Another thing that I don't know how to do because I haven't spent time, but I find it very, very interesting, would be somewhat related to what I've seen in the recent talk of your student, namely PDEs with varying boundaries. So you have looked at problems where you have a state-dependent size of the domain. So this is actually quite similar. There are transformations between transport PDE systems or other PDE systems with fluctuating boundaries, and the same classes of PDE systems with fixed boundaries but with non-constant speeds of propagation or diffusion and so on. So I think there's a lot of opportunity here to address some new problems using this understanding. Your problem that I saw, the one with the Stefan equation, for example, had an ODE and it had a diffusion equation with a state. This is very, very similar, except that it's a diffusion, so it doesn't quite fit this setting, but it would be worth to try to compensate those kinds of dynamics.
Other question? Yes.
So about your negative result on state-dependent delays, does it change if the delays are state-dependent but bounded, or does the problem become easier in that case?
No. So what kills me is not a large delay. What kills me is a large delay rate. And the delay rate is gradient d times f of xu. So I need to be lucky not only in the delay being small or the delay gradient being small, but the delay gradient times the vector field all combined being small. That's a huge assumption. And by the way, it's a Lyapunov-like assumption. But it's not like Lyapunov where V dot needs to be negative. This is Lyapunov-like, like V dot needs to be smaller than 1. And this is a very non-trivial. This assumption is an assumption on the open loop system. In other words, you cannot enforce this assumption by a clever feedback design. You're stuck with it. It's an assumption on the open loop system times the delay gradient.
Questions? So right on the last slide, you sort of got to the point where that I'd been wondering about throughout the talk about delays that might be state-based, but state-based in a stochastic way. So can you give any hints about sort of where you said something about the mean being small enough, but can you give any hints where are the first places you're going to see pushing into that kind of system, or is that just too hard to even think about that?
Well, I really know only what I would do in the case of a deterministic delay. So when you have a time varying delay, I would start from a linear system with a time varying, but a delay with an occasional large perturbation in the delay. The way to approach this problem would be to formulate the delay as a transport PD equation, in which the delay fluctuation would appear multiplicatively. And in that setting, with a Lyapunov function, one could establish stability results in the presence of such perturbations. In the stochastic case, I would have to really look for the theorems that allow me to do such a study. In the deterministic case, those theorems are, we teach them and they're well known, the so-called vanishing perturbations that's in the standard book by University of Illinois alumnus Hassan Khalil. But in the stochastic case, these multiplicative perturbations that are possibly occasionally large, and what they mean if they're occasional bursts, but over the long term, long quiescent periods, I'd have to look for such techniques.
Any other questions? Okay, thank you.
Thank you.